All right, so we're going to continue our discussion of shared memory parallel programming with OpenMP. So we saw last time that the model here is that you have several cores that can do independent computation by a single memory block to which they can all communicate. So they could all work on different parts of the memory and they can see every other part. So if there's a part that core 0 is working on, core 1 can also see that same memory. Now we saw that we can do this by starting from a serial code and adding these pragma OMP pragmas or directives. In particular, pragma OMP parallel starts the threads. So you start on one core, let's say that's core 0, although it doesn't really matter where you start. As soon as you hit this pragma, 8 threads or as many threads as you specify are launched, are spawned. Now we have to say what part of the memory you want these cores to see and which part should be local. Sometimes the thread needs a local variable to operate on that is independent of the ones that the other core sees. So those are the private versus the shared variables. And we have to compile and link with a special flag to make sure that the compiler actually understands this OpenMP business. Okay. So today we're going to look at a thing called reductions. And then we're going to look at all the things that can go wrong with this. Race conditions, performance, and load balancing. So last time we looked at how we can start a parallel thread, a parallel region, and how we can divide up a loop. Today we're going to look at a little bit more complicated stuff. So reductions, what are reductions? And this is an example of a reduction right here on the right. I have a sum. Suppose x and y are two vectors and they are n long. I sum each of their elements element-wise, or I multiply them element-wise and I sum them all up. This is an inner product, a dot product, right, of two vectors. And why this is a reduction is that you can see how every element in the sum could be multiplied independently, so I could easily divide up that work, but at the end of the day I have to sum them all up to one number. So that would mean that all of these numbers, these n multiplied numbers, would now have to be reduced to a single number, hence reduction. Okay, so it's a fairly common thing to have to do. You have a whole bunch of data and you derive one number from it. So we'll look at the serial implementation and then try to parallelize this, and this idea that it all comes together to one variable will be a troubling little feature. So we'll start from the serial implementation. Here it is. So for definiteness, I have to fill these arrays with something. So here are two arrays, x and y of 20 million elements. And I fill them just with the index of their. So element 0 is 0, element 1 is 1, etc. until 20 million. And then there's I'm not quite sure why I do this, but because I have a sort of predictable way of filling this out, I can tell what the answer should be when I do the inner product, and it turns out to be this. And so I produce the dot product by a separate function here that we will try to parallelize, and then I will print out the dot product given by this function and the exact answer, and I'll measure how long it takes. And then the actual algorithm is actually simpler. I pass it two arrays. I will sum up from 0 to n the product of the respective elements into this variable tot, which is then returned. And I kept it a little general, assuming that these could have different sizes. I just sum to the minimum, so I don't use an element that does not exist. That's all that's going on. Okay. So this is typical situation where I have an algorithm and I have a driver routine, and the driver routine looks more complicated than the algorithm, but it's the algorithm that we want to look at. So the setting makes sense. You're just computing in a dot problem. So if I make this and I run it, I indeed find the dot product and the exact answer and the same. And in this case, this serial code produced this apparently in 0.17 seconds. That seems quick, but okay. Now, we want to parallelize this. Seems unnecessary because it's quick, but we will do it anyway. What we could do is parallelize that loop. So just do pragma OMP parallel in front of the loop for, which will divide up, if you remember, the iterations, the I values in blocks between the different threads. So each thread gets a different block. And then I want them all adding up to the same number. And so tot needs to be a shared variable in which they all put their results. Right? So I need a shared variable because that's if they had private variables, they would all be summing up to their own tot, and that is not what I want. So if I run that, if I compile this and then I run it with 8 threads, remember you could set the number of threads with this OMP num threads variable, and I run it, something funny is happening. Get the wrong answer. So the dot product is giving me 5.59 10 to the 20th, and the real answer is 2.6666 10 to the 21. And what's funny is it gives me the wrong answer that differs every time I run. So every time I run, I get a different answer, and none of them are correct. And even worse, so that the answer varies. So it's wrong, it varies, but even worse, it's slower too. So I'm using 8 threads, but somehow, rather than it going any quicker, it goes slower. So it's wrong, it's unpredictable, and it's slow. Throw away OpenMP, go back to serial programming, you say. No. We have to figure out what went wrong here. So something is terribly wrong here. And what's wrong is called a race condition. Sometimes they are more subtle. This one is actually fairly obvious. But what you have, it's a classic parallel bug where you have several threads doing things at the same time and writing to the same resource, in this case, the variable tot. So apparently having this shared memory doesn't mean that everything will just automatically go right. If several threads are trying to access or modify this memory, things can go wrong. So you think, now, why would it go wrong though? It doesn't really look like it goes wrong here. Like, yes, I have different threads trying to update tot, but it's one memory variable, so presumably when I add it, I just add it. It doesn't really matter in what order I get to that point. Why is this really incorrect? Like, why is it not just working? And why is it unpredictable? So to understand that, you kind of have to look at a more simple example and get a little closer to how these cores actually operate on an almost architecture level when they deal with data, when they deal with memory, when they deal with instructions. So suppose that I have the following. I have an initial value of the variable tot is 0, and one thread should add 1, and the other should add 2. So the end result should be 3, right? If we run this in parallel in the same sort of way as we just did, we can see any of the answers 1, 2, or 3. And that's because adding and updating values aren't what is called atomic. This one instruction, this one line of adding to a variable is actually not one instruction as far as the chip, the CPU, is concerned. What actually happens is more like the following. So here's my thread 0, my core 0, whose task is to add 1. Here's thread 1, whose task is to add 2. This is what might happen. First thing that happens with thread 0 is it goes, okay, I'm going to have to modify the variable tot, so I better read what tot is now. And the way it does that is it reads this tot variable into one of its registers. We talked about registers. We've talked about serial programming. Here they become more obtrusive in a sense. So this variable tot is now stored in register. The next part, thread 0, is going to do its addition, so it's going to add 1 to the register. That's exactly what we told it to do, so that's its task. But let's say that at that point, thread 1 kicks in and starts its task, And so it starts reading the value of tot from memory into its register. But the value of tot in memory hasn't changed, right? I've just put it in registry, which is a different bit of memory. So it reads tot equals 0, because the actual memory address that corresponds to tot still is 0. In the next step, thread 0 might be ready to store its results back to tot. So that's good. This did exactly what it needs to do, and it added 1 and got 1 and stores it back into tot. But at this point, thread 1 is only at the step where it updates or it does its addition, so adding 1s to its value of tot that it thinks is 0, which means it gets 2. And then in the last step, well, thread 0 is done, but thread 1 now stores its result back into memory, and its result was 2. And so what we find is that 1 plus 2 equals 2, because thread 1 was the last one to get its result back. So you can see how this is a typical problem with parallel code, because if this didn't happen in parallel, if this happened first and this happened later, the value of tot that was read by thread 1 would just be 1 and everything would work. It's because they do it in parallel that we have this race condition. Exactly. There's always some stuff that it misses. Now that is true here because all the values were positive. If that weren't the case, like who knows what it is. But yes. Yeah. So that kind of explains why it's wrong. We don't get all the results back because while they are being written, old values are being read, and it just doesn't work. But you would still expect it to be faster, wouldn't you? You'd say, okay, this should still be 8 times faster, but terribly wrong. So it's no use. But why is it slower? This is even stranger. Like I'm using all the CPUs, and it's slower. So it comes back again to this idea of registers and cache memory and the hierarchy of memory. Because in this case, all of these variables are trying to store in the same variable in memory, right? So that means that they constantly have to write back to this variable tot. And then other threads have to reread this value. Now, you'd think that that should always be the case. So if we look at those instructions here again, you would think you'd always have to store back into tot. But that's not really true. If you have a loop and you're adding more than one variable, you could skip this storing back and just keep adding. Like if you're one processor, you just take the next value and add that, and takes the next value and add that. Keep it in register. So you don't have to go to the slower main memory. And that's exactly what the compiler will do. When it sees your loop, it'll go, okay, I will just store tot in registry, and I will not copy it back to real memory until the loop is done. And that saves me copying back and forth between memory. But it can't do this if I've parallelized the loop and I have different threads that constantly, then I've said that this variable is shared. If the variable is shared, compiler says, well, apparently the other threads have to see it, so as soon as you're done, you have to copy it back. So in the serial case, the write back to main memory is not necessary, and the compiler will actually omit it until the very end. In the parallel case, because I have this shared variable that I constantly have to update, I basically told the compiler I want this copy back every time, and now it gets slower. Make sense? So we're hitting main memory when we don't really, and that makes it slow. Here's again this idea of the memory hierarchy. So it's not just registers that make this hard. Cache makes this hard too, because that's extra, this extra bit of memory. So the main memory really isn't what you think it is. There's these layers of caches and registries inside the cores, all of which is done kind of automatically or done by the compiler for you, but it makes a big difference in terms of speed, where your variables lie. So let's take this problem one step at a time. Let's first fix the fact that it's the wrong answer, because if we can't even get the right answer, who cares what the performance is, right? and then we'll fix the performance after. So there's a way to tell the compiler not to allow this overlapping of these two regions, because the overlapping that made things go wrong. So there's a thing called a critical pragma that says this region, this particular region, should never be run by more than one thread at a time. It is actually fairly easy to do. They're the same pragma as before, but just before the line that should be only done by one thread at a time, you put pragma OpenMP critical. You'll now make sure that this whole thing, which turned out to be about 3 instructions in the CPU, those 3 instructions never overlap between the different threads. That's what critical means. It's critical, and that's what it does. So we can compile that and run it, and we certainly do get the right answer now. So we get the right answer of 2.66 10 to the 24th, but as you might expect, it's much slower, but not just a little bit slower. It's 13 times slower than the serial case, which is also a little bit surprising, because you would think, well, it's true, essentially we have made this again serial. None of these are happening at the same time, so of course it's not going to be any faster, but isn't that just a serial case? And so the answer is no, it's not, for 2 reasons. One, again, this same copying back to memory. We've said tot is a shared variable, so it has to be copied back, so we have the memory effect. And there has to be some sort of overhead to make sure that these threads that are now running in parallel wait for each other at that moment. So there's a whole mechanism behind it of locks, etc., that make sure that once one thread has entered this region, the others are basically not allowed in. So constantly we're checking, okay, can I go through? Can I go through? So there's much more work done sort of negotiating who of the 8 threads is allowed to go in than pretty much anything else, and that makes it very, very slow. Now there is a way to have the CPU help you with that a little bit by changing from critical to atomic, and this is really a tweak, but an important one to know. There are certain instructions in the CPU where that are so-called atomic, so where this 3-level split up of the instructions does not happen. Now the compiler knows what it can do atomically and what the CPU can do atomically and what it cannot, and it depends on the CPU. But you can ask it, please try and use atomic instructions, so that it doesn't have to do this software locking, doesn't have to keep track of who's where. The hardware does it for you, which tends to be much faster than anything done in software. So it's the same kind of instruction, except for critical you say atomic, and in this case it's an update because I'm updating a variable. Okay. It's the overhead that we're losing here, but we're not really losing anything else, right? So it's just, yeah. It's a bit of both. It makes the update of the variable atomic, right? So I'm saying this is an update, so that should happen as one instruction, and that's so really how it does it is a little bit like a mystery. Like it's like you might want to know, but it really doesn't matter. As long as this happens as if it is atomic, that's all that we really care about. And as long as this is done as fast as possible. So this is sort of saying, do this as fast as possible. Now, for some things, it can't be done. So the reason that we can actually do this is that it's very simple. It's a multiplication. I'm adding, and then I'm putting it in a variable. If this had a sign in it, too bad. If this had maybe several multiplications, I'm not sure if that would work, or several additions, or if I wanted to store this and then use the old value, that's yet another sort of atomic. So there are some details there, but it's always worth a try, because as we can see, the speed up is nice. It goes from, where was it, 2.1 or 2.2 seconds to 1.6. Now, we're not happy with this because it's still much slower than it was. But in cases where you already had some speed up, this can really help. And you're really just asking the hardware, the CPU to use the hardware at its best. Critical is more general. It will always work because it basically enforces it with locks. But it can be very slow. So if it was up to me, I'd tell the implementers to try and replace critical with atomic automatically and just give it a shot. That wasn't the decision of the standard, so we might have to put it in by hand. That's right. So the compiler will complain and say, I can't make this atomic, and then you go, okay, I'll do critical. And yeah.
How does it know what's being up? That's obvious to us. Is it because the plus equal signs there?
That's right. That's right. So
equals the whole thing plus.
If it's equals, it's not an update. So then it would be just a write. And if this was a private variable and I wanted the read to be atomic, I could do an atomic read. And capture is kind of special, where you update and you keep the old value. And those are really the only 4 kinds that you have. So anything that isn't just reading atomically, writing atomically, or updating, which is what this is, or capturing, which is updating and keeping the old values. It's kind of funny, but it happens. This is the most common, I think, because you do it to avoid a race condition in general. But okay, so that's our atomic, but it's still not very performing. So you can be fairly sure that some of this is now done in parallel, except the final update, but it still doesn't seem to be any good. It's still much slower than it was. And the reason is that we haven't really solved this idea of hitting main memory. It's really the memory subsystem, and the subsystem only has, you can think of it as a single lane. It isn't. There's multiple lanes, but think of it as a single lane that all of these cores are trying to share. Then, once you're as fast as you can through that one lane, you're done. So we want to get rid of this idea of copying at main memory, and we're gonna. This is one way to do it, where you say, okay, in my original serial loop, I kept everything in registry, right? In a register. Now all these cores have different registers, but why don't I just let them add their stuff to their own local register? That will be fast, and then at the end, I'll sum up those registers. Now, the way I have to do that in C is because I don't have direct access to the registers. I have to do something that will have the same effect, and that's using local variables or private variables. In other words, I will have local sums in the register. So inside the parallel region, before I start a for loop that is divided up, I will define a local variable called local tot. Because it's locally defined, it's private. But because it's locally defined and private and only used in this section, I can be fairly sure that the compiler is going to make this variable into something that lives just in register. There's no real need for it to store it in main memory. And if there's no need and you switch on optimization, it will put it there. So we can be fairly certain that local tot is going to be in register, just as certain as we were, or that we saw it, that when we did this for the serial case, it put it in registry. How do we know? Because the speed was much bigger than that of the main memory. So here's a local variable that's going to live in register. I will do the sum, but we will add it to this local variable. So this is now local to the thread, which means it can be local to the core, which means it can be in register. It'll just add up these numbers. At the end of the day, we still have to add up those, in our case, 8 numbers to a single number. So we still have a shared variable tot, for which we can do an atomic update of the local sum. But you might note that we do this atomic operation 8 times versus about 20 million times before. So whatever the cost was of doing this atomic update, that should be a lot less. And all of this can be done perfectly in parallel. Okay. So it looks equivalent from a serial point of view, and that should always be the case. And it seems superfluous to have this extra variable. So now we have a case where the serial code seems to be needlessly complicated compared to what's really needed. But only when it's parallel does it make sense to have this local variable. In fact, if we now look at how fast this happens, so the n.local, it is indeed faster. It's about 7 times faster now. That's pretty good, given that this is a very simple operation and all kinds of things can get in the way of perfect speed up. That's a great result. Okay. Does it make sense? It's really the idea that we keep our data local and then only gather it at the very end. That makes this work. Now, this is a very common scenario. Like, these reductions happen all the time. And so, rather than having to do this by hand, the OpenMP standard has a construct for that, to reduce your variables for you and get one value. And it calls these, it's kind of funny, it calls these special kinds of variables. So we've seen private variables and shared variables. These are called reduction variables that you declare kind of like shared and private, but with an operator. It will be plus for us here. And the idea is that it'll do the same kind of thing, or maybe even more complicated things, where each CPU computes its own sum, and then through some sort of algorithm, it comes up to the sum. So it could be just straight summing, or it could be some sort of tiered. Sum 1 and sum 2 are done first, and then sum 3 and sum 4 might be done at the same time. Whatever works, whatever the implementation has. And the way it works is like this. So I have my shared variable here, and tot, rather than being either private or shared, becomes a reduction variable with the operator plus. The code is the same, the answers is the same, and the time is pretty much the same. What this does is essentially what we had done before, right? So this looks mysterious, but what it does when it hits this reduction is it creates local tots. Okay, these local variables, these local sums, they will probably live in register. So this tot inside of the region really only refers to a private variable. It's not shared. But once I end the parallel region, the parallel missing here, OMP parallel for. Okay, once I end the parallel region, it takes those local sums them up with plus. How does it know it has to be plus? That's where this came in. It doesn't really care about this plus. You can do odd things that you shouldn't. But it will plus up, it will sum up the local tots, and then the tot at the end of the parallel region will have the value. So it does exactly what we just did. It might not do it with atomics. We don't really care. It just does it as fast as it can, or as it thinks is appropriate. It's now the library doing it for you, the runtime library doing that for you. But it'll amount to the same thing. So the reason that this works, the reason why you'd have to do this is the same. Local variables. You just don't see it as much. This code, however, is much simpler. So the idea that you have a variable that you sum things to, it becomes a reduction variable, becomes this mechanism behind the scenes, is just reduced to a single extra clause called reduction. What is really nice about this is that if I take away this pragma line, I just have my serial code back. So once you know that you have these reduction variables at your disposal, when you have a loop where there's data dependency, which is what we have here, we're writing to the same variable, but the data dependency is a simple reduction, you can still parallelize the loop by a single line, just declaring that this variable is a reduction. Okay. You can only reduce a couple of things. You can do a product. I think you can do an AND and an OR and a min and a max. Anything that really doesn't depend on the order in which you do it could be reduced. We can't do a minus because the order in which I put in minuses would change things. So there's a restricted set. In OpenMP 4 or 4.5, you can define your own reduction operators if you wanted to. I haven't seen anybody do it, but you could. But plus is by far the most common use. Good. So that's one problem solved. We can now solve race conditions. And we have critical, atomic, and reductions at our disposal. There's another, and we pretty much got perfect speed out, like 7 out of 8 is not bad. There's another case of parallel programming or other performance bug that comes up often, and it's this idea of load balancing. And we saw this already with GNU Parallel. We had serial jobs that might be different durations. If we don't pack them up together nicely, we're wasting time. Now for the loops that we looked at before, there was no trouble with load balancing. Every iteration had the same amount of work, so that when the compiler divides up the iteration space, it divides up the work evenly. It's not always the case. You could have different i's take different amounts of time to be processed. And the compiler can't know that beforehand, right? So it will still assign the I values evenly, but not the work evenly, because the work for each I can be different. So it's a very common case, and so there's actually ways in OpenMP to do load balancing just by adding a couple extra clauses to your directives. Who here knows what this picture is? Yes. So it's not as popular anymore as it once was. It's a fractal. The definition is fairly simple. You have a mapping in the complex plane. These are complex numbers. Take any complex number, square it, and add a, and you get your next complex number. It turns out, depending on the value of a, and not very much on dependent on the beginning point, so you can take the origin. Depending on the value of a, this mapping either makes your complex number explode and go to infinity, or stay finite forever. And the boundary between the set of a values, complex a values, that diverges and converges is called the Mandelbrot set. And it turns out to be fractal. You can zoom in, you get details, very pretty. And so we're going to compute this. So we're going to take, in the complex plane, I think this goes from -1 to 1 in the real axis and -1 to 1 in the complex direction. We're going to take this rectangle in the complex plane. We're going to take those as our a values. And for every one of those a values, we're going to see if this iteration gives us infinity or not. That's a little bit troubling from a numerical point of view, because to know if something really diverges to infinity, you will have to take infinitely many steps, which takes infinitely long, even with a really fast computer. So we're going to do something slightly different. It turns out you can show that as soon as you're outside of a radius of 2, you're diverging. So that is nice. It means that if I start this iteration from any a value and I end out at radius 2 away, I'm done. I know it diverges. The trouble is with the points that don't diverge, that stay in this radius forever. How long should I compute before I know that they really never escape? And the answer is I can't. And the only best next thing I can do is say, I'm going to put an upper bound. I'm going to say, let's try this 1,000 times. And if after 1,000 times you're still not past this radius 2, let's just say that you are finite. And if we're not satisfied with that, we could increase that number 1,000 to do 10,000. But let's just say that that's our criteria. Now, that means that I'm going to have to do about 1,000 iterations for anything that falls inside of the stable zone. Whereas typically you're within 1 or 2 iterations in the unstable zone, I know I am there. So I'm trying to figure out which points are stable and unstable, which one diverge and which one do not. But the ones that diverge, I will figure them out very quickly. And the ones that do not diverge will take about 1,000 times longer. So the computation needed for each of these pixels in the yellow region is much, much larger than in the blue region. But I don't know ahead of time which one is blue and which one is yellow. Now there's a little bit of code in the Mandelbrot set. The main part is where I'm making this map So I'm basically creating the two-dimensional array of color values. And that happens here. And it's an array over it's two for loops, one over I, which is probably the real axis, and one over j, which is the imaginary axis, and compute a complex number somewhere between x min and y min, etc. So that gives me my a, and then I have another function that counts how many iterations there are, which is really just doing a plus b squared, and then checking if it's bigger than 0, with a maximum that is typically set at 1,000. Okay, so this is our main loop, and we'd like to parallelize this. I think that it's a 400 by 400 pixels picture, maybe 800 by 800. I forgot. So a few 10,000s of points that all need to have the same procedure done. We should be able to parallelize that, right? So we're going to try and use OpenMP to parallelize these loops. Here we go. Drag my OMP parallel. That starts my thread. I have a for loop, so I'm going to divide up the work in a for loop. And then I'm going to be explicit, default none. And what has to be shared is my map, my x min, x max, y min, y max, and x. So if I had made any one of these constant, I would not have to specify them as I said before, but this is very explicit. Are there any data? Are we going to get any race conditions for this? You have to worry about that. Who thinks we have some race conditions? We are writing to the same array, right, from all these different threads. Any trouble with this? We're just writing, that's true, but we're writing to the same array. Is there an issue? That's right. So because the indices that we have are different among we're writing into different parts of the array. So that's fine. If we were writing to the same values, we would have a race condition. But because I'm basically dividing out the i's over different threads, they don't write to the same location. And this can cause some performance issues, because it might well be that if you remember our talk about cache, when you read in a bit of memory, you read in a whole cache line. So it is possible that some of these cores are trying to share the same cache line. You don't have to worry about that. The memory subsystem makes sure that the caches stay what's called coherent. But there can be performance issues with that. But we have so many points here that we're not going to really see that. So there might be a performance race condition, but nothing should go wrong. Okay, so there's our loop. Let's see what it does. So the serial case, say, takes about 7.5 seconds. I put 8 threads at work, and it takes 3.34 seconds, or 3.35 seconds. So I only have a speed of about 2.3. Now the reason is quite simple. The threads get different parts of the work. So if I take this, so if my I direction is in this direction, which I think it shouldn't, but in any case, if that's the direction that it's in, then basically each thread gets a slab of this square and computes the color values of this. But now you notice that slab 0 is pretty much all blue. So most of these points, very little work, a little bit of work here. Slab 7, all blue. There's pretty much no work to be done. But slab 4, thread 4 has to compute about 1,000 times more things than slab 7. So what happens is that 0, 1, and 6, and 7, those threads are going to be done in no time. And then we're just waiting for 2, 3, 4, and 5 to finish. And so that's why the speed up is so bad. Effectively, only about 2.3 times things are done in parallel, rather than 8 times in parallel, because we've divided up the unbalanced work, incorrectly. Okay. So we're going to try and do better. Now, we see this picture, and of course, if we had the picture, we'd say, well, we'll just make sure that everybody gets an equal amount of yellow. But the point, of course, is we don't know what is yellow and what isn't. So it's easy to see now that it's unbalanced, but you can't know that. But you might suspect it. So if you suspect it, what can you do to sort of improve on this? So one thing, you can improve in this by changing how the I values are scheduled. When scheduling mean how the work is divided up. So by default, each thread gets a big block. It's bigger consecutive chunk as they can of the loop. But you can change that with the schedule clause. And there's two ways to schedule this. One that's called compile time and one that's runtime, or one that's called static, or one that's called dynamic. Static is just trying to change ahead of time which I value goes to what thread, but deterministically. So it's kind of like, and we'll see how that works. The dynamic case is more like we saw in GNU parallel, where you give a bunch of I values to your threads. Whenever a thread is done with its I values, it gets some more. So it's kind of a backfill kind of schedule. So the two ways to say this is to say schedule static, schedule dynamic, and you can add what's called a chunk size. That's how many I values always stay together. Let's look at an example. So here's the static case. So it's an 400 by 400 picture. So if I take a schedule that is static with a chunk size of 50, what happens is that I take columns, 50 columns at a time, and I assign them to thread 0. The next 50 ones are assigned to thread 1, etc., until I run out of I values, and then it round robins. So the next 50 are given again to 0, the next 50 are given by 1, etc., etc. But deterministically. So this is an assignment of I values to threads that is done at compilation time. I see there are 400 things to do. But with chunk size of 50, that means I have 16 chunks, and I just give them out ahead of time. So basically, in the actual compiled code, thread 0 will know I have to do 0 to 50, I have to do 200 to 250. It knows that. That's not changing. But because it's now more fine-grained, when thread 0 is done, the next I values that it has to take care of are these guys, and there's lots of work to be done here. So because this is a fairly regular but uneven workload, I sort of get it a little bit more balanced. So if I run it with this 50 chunk size static, rather than taking about 2 times faster, it takes 4 times faster. So you can see how this improves things, but it really is, it is by chance. Like there's nothing that guarantees a priori that when 0 is done and it gets its next one, that this would be all blue as well, because we just don't know. So we just improve our chances by making the chunk size smaller, essentially. What helps against this idea of accidentally having still having this load unbalance is to schedule dynamically. And in that case, you just take a whole bunch of small chunks. Again, you can say what the chunk size is. I think it's 4 in this case, I'm not quite sure, maybe 10. But it breaks it up in small pieces and hands them out to the threads. So the first 8 kind of go the same way. They're given to threads, but then whatever thread is done gets the next slab. So I will have 0, 1 to 7. And then the next one, I don't know what it is going to be. It's going to be whoever is done first. Might be 0. If in the next one that is done is 4, then it's 4. So dynamically, I now view these basically as tasks that are scheduled. Each slab is a task that is scheduled. There are 8 workers, 8 threads that could do them, and I just hand them out when they're ready to do another task. So now it can't happen anymore that process 0 gets only easy, well, it could happen that it only gets easy tasks, but then it would be ready for new tasks. So it's a way to keep the processes busy as much as possible. This is exactly the kind of stuff that GNU Parallel did. Right? You had a bunch of tasks and just starts them and gives them to processors that are ready to run. This is the same thing. The only thing that I can do here that I cannot do with GNU Parallel is that I can further subdivide. So I can say what the chunk size is. Now in this case, I forgot what the chunk size was, but I just took whatever the default is, and I get about an 8 times speed of 8.2, which is probably round off and some cache effects. So this is highly efficient. This is great. Now that's not always the case. So you can just start. Now you have unbalanced. You try both of them. Which one gives you the best performance really depends. If it's really very badly imbalanced, so if this was a way more complicated figure, doing this dynamically might only make sense if I do it one line at a time. And if I do it one line at a time, the overhead of the scheduling is going to come into play. Right? It's not completely free. If the overhead of scheduling, or figure out which thread is free now and to hand it its next bit of work, and to do that 400 times, if that is as much work as doing the actual computation, you're not going to get that good a speed up. So sometimes static, although theoretically slower, might be the way to go because you don't pay the overhead. And the only real way to know is to try. You would try on a smaller case than the case you really want, because if you already have solved your case, you don't have to run it again. So in this case, here's sort of the best cases that I could get. And for some reason, the best cases here were with slabs that were 1 long. Remember, that's still 400 pixels, so that's not so bad. The best static one was 101% efficient. The best dynamic turned out to be 103%. This depends not only on your problem, it actually also depends on the implementation. The slides 2 years back would show this roughly reversed because the compilers were older and weren't able to do this scheduling as efficiently as it was, so the dynamic would tend to lose out. The dynamic scheduler in modern OpenMP implementations has improved, and so it tends to work to win, but again, you don't really know what happens. Okay, so the really good news here is that you don't have to do any of the scheduling yourself. You have a loop. You can just say, okay, start load balancing this. Let's just chop it up in different parts just by adding some clauses. So those are two things: the race conditions that really pop up when you do shared memory parallel programming, and the load balancing. And those are the most important things that you need to know about to get performance. There are some other things that are added to the slides. I'll actually forgot exactly what they were, but just some other things that are good to know that you can also do them with OpenMP, but are more corner cases. You might have noticed that we have a 2-level loop. So I always have to have these chunks of 400. What if I want smaller chunks? I can do that. There's a way to say, treat these double loops as one big loop. Just collapse them and chop it up as one big iteration space. That's this collapse thing. I haven't really found it to be too useful, but it could be. You can do some other more fine-grained things. You could, let's forget about these ones. You could have sections. We've just seen loops, and that's most of what you see in scientific computing. But sometimes there might be 2 tasks that are wildly different that can still be done at the same time. It's not a loop. It wouldn't make sense to write it as a loop and then say, if I is 0, write to disk. If I is 1, produce a graphics on my screen. Although that can be done in parallel. So you can do that with sections, or you can do it with tasks, which generalizes this idea of the scheduler. So rather than a loop being converted into a bunch of tasks, you just say, here's a task, here's another task, here's another task. Put it on the queue. Wait until there's a thread ready to run it, then run it, and so this is almost doing it by hand again. So if you don't have to use it, don't. But if you need to, I don't know, traverse a binary tree, and there's no loop, you're just following pointers. Doing this kind of stuff can help. We just saw collapse, so that's. There are cases where OpenMP doesn't work well. We saw how we could get performance using the reduction variables. What if we have something more complicated that uses shared memory really, really intimately, and we have to do this copying, and then the algorithm just doesn't lend it to any other way? We don't want this to be parallelized, so we could just not do pragmas. Sometimes it depends on how many how many values we have. If our iteration space is large, it makes sense. If it's not, it doesn't. So you can do conditional OpenMP that says, if n is less than 10, then don't do OpenMP. If it's bigger, please use more threads. So it looks like this. If it's a tuning thing, so it's good to know that it's there if you need it. There's other things you can do, dependency. So once you really go into writing your own tasks, which few people will do, but if you do, then you can imagine that there might be dependencies. You might have to have task A done before task B can be done, because A produces a variable result that B basically consumes. You can do that. You can nest parallelism, so you could have one of those tasks, say, or inside a loop, you could say, okay, now I have another loop in there, I also want it parallel. You can do that, but now you have to worry about the fact that you have a finite number of threads, so it becomes a little bit tricky. You can do locks. So we talked about locks sort of loosely when we did the critical. You can be specific in your own locks. You can say, okay, I want this region to be protected by a lock, but maybe only threads 0 and 3 cannot enter the lock, so they check for the lock, and 2 and 5 are fine to enter. You could do fine-grained locking mechanisms and authorizations and stuff like that. You can use vectorized instructions with SIMDs. You can tell threads where they should live. So you could say, okay, thread 0 should always live on core 0. Thread 1 should live on a 1. You might wonder, isn't that always the case? And it turns out it isn't. The operating system will sometimes take your thread that was running core 0 and put it on core 8. Why? Because core 8 wasn't doing anything at the time. So that really only matters when you have load imbalance and when you're not using your cores full time. Again, a bit of a corner case in most computational science. And then there's a whole new area of OpenMP, which we haven't talked about at all, but it goes away from this idea of shared memory, and that can access compute devices, which you should think of graphics cards, Xeon Phis, other kind of accelerators that aren't actually seeing the same shared memory, but might live on the same node. So there's a sort of an intermediate between the shared memory parallelism, one node, all cores see the same memory, separate nodes, which is distributed memory, where you have to send messages, and then this idea of you have a node, and on top of that I plugged in a card, a compute card, say a graphics card, and I want it to do some computation for me. It's not quite the same model, and so they've put this in OpenMP, but it's kind of a different model, because now it's not shared memory programming anymore. So we're not going to talk about that much here, but it's in there too. So this is one of the reasons why I say if you want to read the standard, read it before they added all this. Read OpenMP 2, and you will read the details of private and shared and all of that. I wouldn't recommend reading the 400 pages of standard that comprise all of this. It's very confusing. Questions? Yeah. Uh-huh.
Let's say it's the same.
Yes. If it's the same, if you can guarantee it's the same value, you probably don't have to do it from all of them. But if it's not the same value, then basically you don't know what's going to come out, right? So the last one would win.
Oh,
I see what you mean. Yeah. Yes. Strictly speaking, the standard doesn't guarantee that you get any of these values out. I haven't seen anything violate that, but you could imagine that 8 threads are running at the same time, but there's something in the final joining of the threads that destroys whatever you did, because who knows why, right? So the standard doesn't guarantee that that result will now be correct. It will be equal to any of these 8 officially. Yes, so it doesn't guarantee that. So I don't know what kind of architecture would ever really behave that way. I have not seen it, but it's still better to not rely on that if you want to be absolutely correct.
So
Yes.